We are moving past the single-pass prompt. AI is entering the agentic era, where models actively reason through problems and execute multi-step workflows and learn from their own actions in continuous, iterative loops. This shift creates two severely distinct environments for hardware. Training a trillion-parameter frontier model requires pushing massive, unbroken volumes of data through an ever-expanding cluster. Conversely, serving a swarm of active AI agents requires processing countless, unpredictable micro-requests with near-zero latency. You cannot optimize a single piece of silicon for both extreme throughput and ultra-low latency simultaneously. The physical demands of memory and bandwidth directly conflict. To solve this, Google's 8th-generation Tensor Processing Units split the architecture entirely. The new generation is intentionally bifurcated into two highly specialized chips, the TPU-8T and the TPU-8i. The TPU-8T is the training powerhouse. Its architecture is strictly engineered to maximize compute throughput and massive scale-up bandwidth. The TPU-8i operates as the reasoning engine. Its design prioritizes massive memory availability and ultra-low latency for inference workloads. Both designs rely on full-stack machine learning co-design. The hardware is customized at the silicon level to map directly to the specific software architectures and network requirements of modern models. Processing the complexities of trillion-parameter AI requires discarding the general-purpose hardware model and embracing divergent, specialized silicon. The TPU-8T architecture's primary objective is compressing the frontier model development cycle from months down to weeks. To execute this, a single superpod scales up to 9,600 chips, all connected to a unified 2-petabyte block of shared high-bandwidth memory. Equipped with double the interchip bandwidth of the previous generation, this delivers 121 exaflops of raw compute. By utilizing the mu-verbo network with pathway software, the 8T achieves near-linear scaling for up to 1 million chips within a single logical cluster. Operating at this scale introduces a severe physical constraint. When you network tens of thousands to 1 million chips, hardware failure is not a possibility, it is a statistical certainty. Every single dead link, every network stall, or checkpoint restart halts the cluster. At frontier scale, those interruptions translate directly into days of lost, highly expensive training time. This exposes the critical gap between raw throughput, your theoretical maximum power, and goodput, which is the exact measure of useful, productive compute time. Google engineered the TPU-8T to target over 97% goodput, maintaining near-constant productive compute even as physical components degrade over time. The first layer of defense is real-time telemetry, which instantly identifies faulty interconnect links across tens of thousands of chips. This visual demonstrates optical circuit switching. When a failure is detected, instead of relying on a slow software workaround, a network of optical mirrors physically bends the light path around the dead chip. This hardware reconfiguration happens instantly and autonomously, with zero human intervention required. Because the physical pathway is corrected on the fly, the active training job never drops or stops running. Keeping the processors running solves only half the problem. The system must ingest data fast enough to keep them fed, which is why the architecture includes TPU Direct. Integrating storage access that is 10 times faster than before, TPU Direct pulls data straight into the processing unit. The massive cluster never idles while waiting for the next batch of training data. At the bleeding edge of AI development, raw compute speed means nothing if the system constantly stalls. Autonomous fault tolerance is the multiplier that actually turns theoretical power into real progress. The TPU-8i carries the exact opposite mandate. It is designed to handle the rapid, collaborative, and iterative work of specialized agent swarms, where latency dictates viability. For inference workloads, the primary bottleneck is not raw processing power, it is the memory wall. If a processor finishes a calculation and has to sit idle waiting for the next piece of data from off-chip memory, it creates lag. When thousands of AI agents interact in complex workflows, those micro-delays magnify into massive system inefficiencies. This diagram shows the 8i's hardware solution. To break the memory wall, the chip pairs 288 gigabytes of high-bandwidth memory with 384 megabytes of on-chip SRAM placed directly next to the compute core to absorb rapid, continuous data requests. This 384 megabyte capacity is sized exactly to the key value cache footprint of modern reasoning models at production scale. Perfect sizing prevents off-chip retrieval, keeping the entire active working set completely on chip. Modern architectures, particularly mixture of experts models, introduce a distinct networking challenge. In an MoE model, individual tokens must be rapidly routed to highly specialized experts across the network. This demands extreme interconnect bandwidth to prevent data traffic jams. To support this routing, the 8i doubles its interconnect bandwidth, pushing 19.2 terabits per second. This interconnect traffic routes through the new hierarchical board-fly topology. The system builds from a 4-chip block into a fully connected group of 8 boards, expanding outward until 36 groups form a single, massive pod. This specific geometry compresses physical space, reducing the maximum network diameter by more than 50%. Because the travel distance is halved, the entire pod operates as a single, low-latency unit rather than a fragmented cluster. Finally, to push latency down even further, Google introduced the on-chip collectives acceleration engine. By offloading global network operations directly to this engine, the chip significantly minimizes lag, reducing on-chip latency by up to 5 times. By destroying the memory wall and eliminating idle processor time, the new 8i delivers 80% better performance per dollar. Businesses can serve nearly twice the customer volume at the exact same cost. Generating a 2 times improvement in performance per watt over the previous generation requires optimizing far beyond the silicon layer. For the first time, both the 8T and 8i run on Google's custom Axion ARM-based CPU hosts. By utilizing a non-uniform memory architecture, Google achieves strict physical isolation for these components, optimizing the full system for superior processing performance. This full-stack approach is critical because the ultimate physical ceiling of the modern data center is not chip supply. It is raw electrical power. The performance densities generated by the 8th generation TPUs mathematically outpace the thermal limits of traditional air cooling. To sustain this compute load, the hardware relies on 4th generation liquid cooling technology that is co-designed directly alongside the chips. This extreme vertical integration culminates in the AI hypercomputer. It unifies purpose-built hardware, massive storage, optical networking, and open software frameworks like JAX, PyTorch, and VLLM into a single cohesive stack. It also provides developers with bare metal access, completely bypassing the computational overhead created by virtualization. In the agentic era, isolated compute power is a bottleneck waiting to happen. Training and serving the next generation of AI requires a custom end-to-end infrastructure meticulously engineered to map the physics of the silicon directly to the logic of the model.